Well, now let's go ahead and turn our attention here to example number 1 and try to use what we talked about in the opening motivation in a specific context. Let's go ahead and consider the function of f of x equals x to the 6th power. Now again, I should be able to see that for certain values of x, this is going to be again very easy to compute. Plugging in 0, plugging in 1, heck, even plugging in something like 2 would be pretty easy. So in fact, I'm going to be asked here to find a linearization of the function f at x equals 2. Okay, well again, that just means find a tangent line. Now it can be helpful at times to be thinking about a picture of the function that we're working with. Now x to the 6th, very surprisingly, is going to look almost like a basic parabola. It's just actually a lot wider and a lot flatter near the beginning. So this is actually what I'm going to be looking at here for my function f of x. And if I'm going over here, say, to the value of 2, and I'm building a tangent line right here, okay, again, this is just a rough sketch of the picture, but I should expect that I get a tangent line that's going to have a positive slope and is going to have a negative y-intercept. But this is, again, just my linearization. So I just want to find this. Okay, so let's see. I'm going to need to find the coordinates of my point, and I'm going to need to go ahead and actually find the slope of this tangent line. So I can note that if I go to my function f and I plug in 2, I'm going to get 2 to the 6th power. And 2 to the 6th power, you could double check me with, is actually 64, right? You just multiply 2 up a bunch of times. We can also see here that f prime of x is going to be 6x to the 5th, and that's then going to mean that if I did f prime of 2, I'm going to get 6 times 2 to the 5th power. Now 2 to the 5th is 32, and if I multiply that by 6, I get 192. So I get some big numbers kind of happening here, but it doesn't change anything about constructing my tangent line. Notice here, I can then say that the linearization, or the tangent line, is, and I'll write this as L of x minus my point, which is 64 for my y-coordinate, and then I have my slope of 192, x minus the x-coordinate of 2. Now I could go ahead, I could simplify this down to just have it say L of x equals, and I would get 192. Notice in here I'm going to get 192 doubled. That's going to turn into a really, really big value, and I could simplify this down and write it in, simplify out what 192 times the negative 2 is, and then add the 64 over. But for the sake of argument right now, I'm actually going to leave this here in this kind of unsimplified form, and you'll see why I'm going to do this in a moment. But I'm just going to leave it right here. This is going to be the equation of my line. Now one thing that may have seemed a little odd here is that instead of writing y minus the 64 on this side, I just started by writing L of x. If you still want to write y, that's totally fine, but typically in my solutions you'll see that I'll just jump in with L of x, since that's the notation that we were using in the definition above. Well, now let's take a look at what it is that we want to try to do. We want to use our answer from part A, that is our blue tangent line here, to approximate the number 2.01 raised to the 6th power by hand. Okay, well, again, this shouldn't be too terribly difficult, because if I want to actually calculate this, I can think in the picture that 2.01 is going to be like somewhere right around here. And if I was to go up and plug that number into the black f of x function, I get a dot like right here. Right? This is my mystery y value. And if instead I was to plug that 2.01 into my blue function, you can almost hardly tell a difference in that right now, right? It looks like plugging it into the blue function is going to return almost identically the same value as plugging it into the black function. And this is our idea. This is how we can tell that we're getting to a value that's actually going to be really close to our actual value. So to do this, I'm going to go ahead and just state the following. So I'll say that we see that 2.01 to the power of 6 is identical to going to my function and plugging in 2.01. Right? That's what it would look like, 2.01 to the 6th. And I know that my function is roughly the same as my line, my tangent line. And so if I plug that point into the tangent line versus plugging it into the function, I should get almost the same value. So of course, I can now go ahead and replace x in my formula here with this value of 2.01. And it's at this point where you might see why it would be advantageous to not have simplified this tangent line anymore. Because now notice how easy it's going to be to do the subtraction and resulting simplifications. I'm going to end up with 192 times 0.01 plus 64. Now, 0.01 is 1/100th, right? It's moving my decimal over on this value 2 places. So I'm going to get 1.92 plus 64, or ultimately I'm going to get 65.92. So if someone asked me, Kyle, no calculator, what is 2.01 to the 6th power? I would guess it's roughly going to be the same as 65.92. Now chances are is I didn't hit it perfectly, but if I look at my picture, gosh, it seems like I'm really, really close. So let's go ahead and actually see how close we are. This is what part C asks. Can we use a calculator to find out how far our approximation is from the actual value? So I'm going to go ahead here and state the actual value is going to be, and let's pull up a calculator here. So I'm going to go ahead and do 2.01 to the power of 6. So my value is 65.9441606. All right, so let's see what we have here. This would be, again, 65.9441606. And our estimation was 65.92. 0.00000 if I line up all the spots. So I mean, like, if you look at that, we are already really, really close. If I was to go ahead and do a little subtraction here, and you could actually double check this, I think I would get down to a final value of 0.0241606 Right, like, I am actually going to be so incredibly close here to the actual value. That is, if I took my calculator here and I actually said, let's subtract off what we did, right? There's the value that I get back. So we are so incredibly close here. It's amazing. So we could also start to think here, though, about the fact that did we know if our answer was going to be an overestimate or an underestimate? Now this actually isn't too hard to see because I can take a look at the picture. I should notice where that red dot is because that was the dot for the actual value. And if I was instead plugging in 2.01 to my tangent line, I should be able to see that my tangent line should fall a little bit beneath that function at that point, right? The tangent line's below the function here. And so I should know that this value immediately is an underestimate, which is exactly, again, what we're seeing here.